So let's continue where we left off from the last video. We have the 24 bits of the mantissa here. So the first bit is the hidden bit, and then we have the other 23 bits. Now we said that we're going to shift this to the right, and we're going to take a copy of the bits that get shifted out. So we have the copy of these bits that get shifted out here, so we have another 24 possible bits whenever we shift all of these out. So we've got access to all of the information we require. So you might think that that's us pretty much done. So if we were to head into the spreadsheet, we could say that we have access to all of these bits here, which were the top 24 bits of the mantissa, and we have access to all of these bits here, which are the other 24 bits that could drop off to the right. And then we would be able to say then, whenever we produce the final sum, so this is the final answer here before the rounding, which is row 23, then in this row 23, we're going to have this value here, which is going to be our least significant bit. We're going to have a value here, which is the guard bit. So the guard bit is just the first bit that drops off the end. So we can just take a copy of this and put it here. So that's the guard bit. And then what we do is we would OR all of the remaining bits. So this is the remaining bits here. And if we OR these together, then it's going to give us the round bit, which is going to be this one. So we're going to have our least significant bit here. We're going to have our guard bit here. And we're going to have our round bit. And we could then use these and put them into the truth table that we've seen in a previous video, in order to work out whether we have to add a value of 1 onto this to get the final rounded answer or not. But there is actually an added complication, and that is that these bits get shifted whenever we do the normalization. So if we head into the Logisim, you can see here that we have this normalization function. Now, we're only looking at the far path at the moment. We'll deal with the near path once we've covered this. But if we drop into this normalization, remember, we're going to have to shift the mantissa either by a value of 1 to the right, that is, we're going to divide the mantissa by 2, or we're going to shift the mantissa 1 to the left, that is, we're going to multiply by 2. Or there is an option, of course, of the mantissa remaining exactly as it is. So we can have the mantissa staying in position, or moving 1 left, or moving 1 right. And we're going to have to take care of that within the rest of the floating point adder and subtractor, because this is going to change the position of the least significant bit, the guard bits, and the round bit. And let's see how this change is going to happen. So if we drop down into the adder and subtractor, and then head into the shifter, now we're interested in this section here. So this is going to control the positions of our least significant bit, the guard bit, and the round bit. So in the far path, we've got 3 options. We've got first option, which is we add 2 numbers and we don't have any ripple. That is, we add 2 numbers together and the final answer still sits in the same exponent range. It hasn't gone up into the next exponent range up. So in that case, our least significant bit, our guard bit, and our round bits remain in position. Now the second option that we're going to have here is we can have an addition, and when we add the 2 numbers together, the final answer is in the next exponent range up. So that means that the exponent is increased by a value of 1, which in effect is times 2. So therefore, in order to normalise it, the mantissa has to be divided by 2. That is, we're going to have to shift the mantissa to the right. So if we were to head up here and look at this example here, where we shift the mantissa to the right, we would have the value here for the first value, which is going to be our guard bit, and then we would have the other 23 bits, which would be our sticky bits, which we would OR together to give our value for our round bit. But now, if we're going to shift this to the right, then this value here would drop off the end, and the value that was in the guard bit would now be part of the sticky bit. So in effect, the guard bits would be OR'd along with the rest of the sticky bits. But it would mean that also that the position that we have here for the guard bit, well, it's going to have to come from the final answer of our addition and subtraction. Now, I won't show you where that comes from just now, but we'll go in and we'll show you that just in a minute. But we're going to have to drag in the least significant bit from the answer. And of course, the previous value for the least significant bit is going to become the new significant bit. So for example, in this example here, we're going to be shifting everything to the right. So when we shift everything to the right, it means that all of these values here, all of these have to get shifted to the right by 1, and the last value here drops off the end. And if that value drops off the end, then it means that the guard bit then drops into the sticky bit, so the guard bit gets OR'd along with the rest of the sticky bits. And the value here for our guard bit then comes from the final answer. So the final answer down here is the least significant bit, so this least significant bit must drop into this position here. So it's this one here that drops into the guard bit position. And of course this value here, which was one away from the least significant bit, now becomes the new least significant bit. So that's the process that we have to go through whenever we do an addition with an increase in ripple. So again, what we'll do, I'll talk through the third one and then we'll go back to the second and we'll show you exactly how we build that. So the other option we have is a subtraction with cancellation. So we only have one, and a subtraction with cancellation whenever we have an exponent value which is a difference of 1. So we have the possibility that the exponent will decrease by a factor of 1, that is, it gets halved, and that case then we're going to have to increase the mantissa by a factor of 2. That is, we're going to have to shift the mantissa to the left. So again, if we look above here and we look at the values we've got, if we shift the mantissa to the left, it means that all of this rounding here has to be shifted to the left. So if all of this gets shifted to the left, what happens is we are going to pulse in another 0 here. So from outside here, a 0 will drop in here. The value here, which was the first value for our sticky bit, jumps into the position for the guard bit, so that becomes the new guard bit. And it means that the guard bit here then is going to have to jump into the value for the least significant bit of the answer. So again, if we look at it in terms of the spreadsheet, all of these values here are going to have to move to the left. So whenever they move to the left, we drag this 0 into this position, and then the sticky bit here, the first sticky bit, then becomes the new guard bit, and then the new guard bit is going to have to jump into the least significant bit here. And what was the least significant bit jumps into this bit here, because all of these, say, are shifted up to the left. So we have to do those two options within Logisim. And it makes it a little bit difficult within Logisim because we're dealing with two separate registers. We've got a 32-bit register for the 24-bit register for the top 24 bits of the mantissa, and another 24-bit register for the rounding values that we are interested in whenever it gets shifted left, when it gets shifted to the right. And it makes it difficult within Logisim to build that, but I'll show you the actual build just in a second. Now the other option here was option 1, which was the round bits, just everything remains the same. So let's talk through option 2 and then option 3, and that will cover us for this video. So in option 2, the mantissa gets shifted to the right. So this is our option 2. We take our round bits here and we take a copy of them and we bring them in here. So we're going to shift it to the right by a value of 1. So whenever we shift it to the right by a value of 1, we said that the least significant bit just drops off the end and we're not bothered. But now the most significant bit that we bring in is actually the least significant bit of the final sum. So we have to get this from the final sum. So I'll show you where that comes from just now. We head up in here and we head in and you see it says least significant bit here. I'll head in here and it's just brought it in up here. So this is the sum. So this is the 24-bit sum. And what we're going to do is we're going to take the value for the least significant bit, which is in effect this bit here. So this is the bit here, which is the least significant bit, which is 0, which is going to be dropping into the guard bit. So again, from the spreadsheet, you can see we're going to be shifting this bit here up into the guard bit. And that's what we've done here within the circuit. So if I head up into the top level, you'll see we've taken that least significant bit and we've brought it up into the shifter. And this least significant bit comes in here and it gets injected in at this point here. So this is the shifting of the least significant bit into the guard bit. Now the other one here is option 3, and you can see I've got option 3 here. So we take the round bits and we shift the round bits to the left. Now this is quite straightforward as far as the rounding bits, because it just works through and it will shift this here to the left. So when we shift it to the left, it will just drag in a 0 and this value here will just drop into this position. Okay, so that's the sticky bit dropping into the guard bit position and dragging in a 0. But then we're going to have to deal with the least significant bit, because now the least significant bit, we're going to have to take this value here and we're going to have to shift it into the least significant bit position. So we'll have to take a copy of this value. So now we've got a copy of the value and that copy comes out here. So this is the 24th bit here, which we're going to use to inject in the guard bit, injecting into the least significant bit position. So where do we inject this? Well, we have to inject it down at the answer. So again, if we go to the top level and we head down to where the answer is, and you can see that we've got that go, which is, it's really the guard bit, which is being going to be used as an injection, and we place it in at this position here. So that's it there, and it heads into the normalization. Now we're going to have to inject it, and we inject it down here. So you can see here that we're going to have a final value here for our addition, and we're going to have to take the least significant bit of that and we're going to have to inject this value into that least significant bit. So in effect, we're taking this value here, which was the guard bit, and we're injecting it into the least significant bit here. So we inject it at this point here, and that's where that injection takes place. Now there's options here as well to choose, but we'll talk through that just in a minute, because we haven't talked through how we're actually going to multiplex any of that, but that's where that bit gets injected. So that covers the process of shifting the values left or right by a factor of 1 depending on the normalization. So that's probably the most awkward and difficult section to try and understand, but with floating point numbers and floating point units, as you've probably became aware, that the devil really is in the detail. So that's enough for this video. In the next video we'll go ahead and we'll see exactly how we're able to multiplex this, as actually make the choices for each of the multiplexers here. So thank you for listening. I'll get you on the next video. Goodbye.